Okay, welcome to MAT211. We're going to take a look at section 4.1, looking at systems of two linear equations and two unknowns. During class today, I had a technical issue that I need one additional adapter, so I'll get to work on that for next time, but we will record each class session as we go, but this will be a special recording of the content. So let's go ahead and move forward. So what is a linear equation and solutions? Well, if you remember from algebra, linear equation is typically, we think of as y equals mx plus b, or the business form of that equation typically starts with b, then you add the mx, and that's what your y is. So that's a linear equation primarily. The thing we're going to focus on is that there are two unknowns, x and y. So these are our variables. X is some amount of stuff. Could be a dollar amount, could be a quantity amount, and y is an amount of other stuff. Okay. So here's an example. We have $3 in our pocket to spend on either snacks or a drink. Now, this is a little bit of information, but the $3 is not a variable. It's a set amount. So that is going to be what we call a constraint, something that limits what we're able to do. But what we're spending on are snacks and drinks. So it's either we're going to want total number of snacks we can buy, total amount of drinks, or it could be the dollar, because we're only going to get one snack. You know, you shouldn't eat too many snacks, right? One drink is enough. How much do we spend on snacks? How much do we spend on a drink? So let's look at the rest of the question. And they tell us specifically that X is going to represent the amount you'll spend. So it is an amount, but it is a dollar amount. Or, you know, in the US, we'll assume in dollars. Y represents the amount you'll spend on a drink. And so we can say that X plus Y, the amount that we spend on snacks, plus the amount we spend on drinks, should equal $3, or less than $3. We can't spend all our money, right? So typically we want to define our variables: dollars on snacks, and y is the dollars on the drink. And so this is oftentimes helpful when we go through solving questions. There's also, there's various ways we could define this. Also, we might want to say we can spend $1 more on snacks than drinks. So then you would say this, that if you take what you spent on the snacks, subtract the drink, that you'll have $1 left over. So it's a linear equation. It's, again, just another example of what might be done. So linear equations and two unknowns. It's an equation that's been written in this form. So this is what we call general form, standard form. Notice this can be solved for y, and that might be the y equals mx plus b. So we would subtract ax from both sides. So you end up with by equals c minus ax, and then we would divide both sides by b. So we can rewrite this as y equals c over b minus a over bx, and you know, y equals mx plus b form. This is slope-intercept form. So either one is useful. The numbers a and b, and c as well, those are real numbers, they're amounts. And a is the coefficient of x, b is the coefficient of y. Now what we're going to see is that this general form is in many ways much more useful for us in what we're going to be doing than the slope-intercept form. Because eventually what we do is we're going to use matrices, which is basically just using those numbers a, b, and c. But that's a little aside. Okay, The solution is values as ordered pairs of x and y that satisfy this equation. So we plug in a value for x and plug in a value for y, and in this case, after doing the calculation, we should end up with c equals c. So that would give us whatever x and y are. So we'll look at some examples of that. So sometimes, okay, so with linear systems of equations, they're straight lines. What we're also going to see is that uh, as we get ahead and we're dealing with two lines, our solutions will be the places that our two lines intersect. So two lines can only intersect in one place at most. So there'll be one solution. Uh, we'll see that it's possible the two lines become one line, or they're actually one line, so that's an infinite number of solutions. Or it's also possible to have parallel lines which have no intersection and no solution. So here we have 3x minus 2y equals 12. We notice the coefficient in front of the x is 3, coefficient in front of the y is negative 2, so they've identified those. And then they just picked a pair that 4, 0 is a solution, because if you plug in 4 for x and 0 for y, you get 12 minus 0 equals 12. And so that's a check. Yes, 12 does equal 12. If you want to determine all solutions, think, okay, what we are going to do is we're going to do what's called parameterize. They'll spell it correctly later on. My spelling sometimes is a little messy, but we're going to parameterize in terms of either x or y. So what we're going to do is we're going to solve this one for y, which will parameterize it in terms of x, which is kind of, it's always backwards. So we're going to subtract 3x from both sides. Gives us negative 2y equals 12 minus 3x. We'll then divide by negative 2, negative 2, negative 2. So we get y equals negative 6 plus 3 halves x. And so what we're able to say is that all the solutions will be a value of an x. And again, this is why x can be many different things, right? Infinite number. And y, what is y going to be? In terms of x, it's going to be, let me rewrite this as 3 halves x minus 6. This equation becomes our parameterization. So this is actually represents an infinite number. Plug in a value for x, plug in the x here, and do the math, and you'll get a number for y. You'll get an x and y pair. And we'll see, what was that last solution? They gave us 4, 0. So if you put in 4 for x, you're going to get 3 halves times 4 minus 6. 2 goes into 4, that's 2. 2 times 3 is, you get 6 minus 6. You get 0. So we can see we can get a particular solution by plugging in a value for x. And we checked this one earlier. We could plug in different values. We could plug in 3 for x, and we get an answer. We might get a fraction. That's fine. But this here is how we're going to write all solutions. Okay, and they do it here, parameterized. In terms of x, give me the x. We can figure out the y. X is arbitrary, so that's an infinite number of solutions, general solutions. Parameterized, so I guess my spelling probably wasn't too bad. And if you see, if you're not sure, just kind of make it either mumble or squiggle. So general solution, that's here, general solution, all possible particular solutions. So plug in a particular value, you get it. And then in doing so, we've set up a parameter. The parameter is x. Give me x, I can get you y. So parameterized by x. We could also have solved it for y. Solved it for x, and then we could parameterize it in y. And it just depends. Both work just as equally well. It just depends on what we want to do. But just let you know, both can be done, and both will be done. Here's a graphical solution showing all the solutions, and all the solutions are on a line. That's why it's linear, right? So plug in various x values, you get various y values, you get this line. And in this course, we're going to ask you to rely heavily on graphing calculators because the graphical solution gives you, in my opinion, a very good view that, oh yeah, there's a lot of different solutions here rather than just the abstract symbols that we write. Okay. Particular solutions. So let's keep moving forward. Particular solution is going to be kind of like what we did. It's a number. It's um, in this case, if we have just a single equation, then they're going to be all the points on the graph of the equation, which will be a straight line, right? Because we're dealing with linears. This is also parameterized. We can parameterize it by, say, for x, by solving for y, and then just like we did. Again, I just point this out because it's in the text. You can parameterize by y. What you do is you solve the equation for x, get x equals that, and then if you give me y, we can plug it in. Again, just depends on what you're, and sometimes it's hard to, it's arbitrary what we call x and y. We could switch them around. And that's why it's important to define your variables because that snacks and drinks, we could have easily called y the number of snacks and x the number of drinks. So we could switch it. There's no hard and fast rule on that one. So here's just an example. We have 2x plus y equals 4. I think we looked at this earlier, if not, but there's a particular solution. If you plug in 0 for x and 4 for y, that works. If you plug in 1 for x and 2 for y, 2 plus 2 equals 4, that works. And there's a lot of others. So many, infinitely others. So the way we show all those solutions is we parameterize. And again, typical, we will solve for y and parameterize in terms of x. And so when we do that, we come up with all our solutions, x comma negative 2x plus 4. So we plug in a value for x, we get the value for y. We could have just as easily solved for solve for x, and we get a different formula, but it's the inverse. Hopefully you can kind of see. So instead of multiplying by negative 2, we're dividing by negative 2 and such. So anyway, this will work as well. We'll get the same. If you were to graph these are the same line, same solutions. It's just a different look, right? Parameterize in terms of x or parameterize in terms of y. So now let's get into what's involved in a system of two equations and solving these equations. One of the tools we're going to use again and again is something called elimination. And that's a process where we basically add both equations together and hopefully one of the variables will eliminate itself. And in this case, we see we have a positive y and a negative y, so they do eliminate themselves. Now let's just take this equation, x plus y equals 3. Could I add 1 to both sides of this equation? Well, yes, because it's an equation, I can, as long as I do the same thing to both sides of that equation, I maintain the equality. So x plus y plus 1 is equal to 4. This is still a true equation based upon what we started with. What we're going to do is we're actually going to add these two equations. It's like really we're going to add 1 to both sides. But in this case, this equation also says that x minus 1 equals 1. So x minus 1, have to see, is another form of 1. So really we're adding 1. When we add two equations together, it's legal to do because we're thinking of it as if we're just like adding 1 to both sides. But over on this side, when we add 1, we add a different form of 1. X minus y is 1. Okay. So 3 plus 1 is 4. When we add these together, x plus x, like terms, so that's 2x, positive x minus y, that's 0. So We could put plus 0, but we could leave it blank, right? Plus 0 is not going to add anything. And then what we do is finish solving for x by dividing by 2. So that's where elimination works, is we get it down to one variable, and then we can finish the solving. We've solved for x. To get y, we have to go back to one of these equations. And let's just take the top one. Actually, it'll work in both equations, so it's always good to check them both. But I plug in 2 for x, and then I can solve for y. So x equals 2, y equals 1. That's my particular solution that I end up with, 2 comma 1. I can write it that way. We can write it this way. And then if you check here, final check, does that also work? Well, if x is 2 and y is 1, does that equal 1? 2 minus 1, 1 equals 1. Yeah, that checks. So it's good to do a double check on everything. But that's what we're doing. So we have two equations with two unknowns. We will typically be able to get a solution. Not always. We'll see. There's a couple cases where this doesn't work. But what this is it's, if we were to graph these, again, one way of doing this is solving both for y. We put in a graphing calculator, and notice our solution here is the point 2 comma 1 is the intersection point of the two lines. That's graphically what the solution will look like. I like the graphical solution. It's, you know, you see exactly what's going on, but it also tells us if we stray to the left or the right, how quickly we get away from our solution. Because sometimes in the real world, the business world, we can't exactly, you know, achieve this to get that. That's where, you know, maybe the prime solution, the perfect world solution, but sometimes we can only get like 1.9, and so we get close, but that's a little bit off here. So, you know, we make adjustments, but that's where the graphical solution will help us. We can do it either way. We can graph it, we can use elimination, and I think there's two others. There's a substitution and one other way. So here we go. Let's go ahead and look at solving this one. Can I get that thing out of the way? Okay. Changing one equation. So we can use elimination here. In class, we went ahead and graphed this first. Let's, in this little take, I'll go ahead and do this with elimination. So we've got these two equations. To eliminate, we want to focus on one of the variables. Let's just go ahead and try to eliminate x. And what we need to do is we need to get this and this, the x values, the coefficients, to both be the same number but one opposite. So this is 4. If I could make this bottom one into -4, then I'd be able to eliminate, right? That's what my thinking is. But what I'm going to have to do that is, remember, we have equations. I can make, if I multiply by -2, I will get the value I want. But in order to do that with an equation, I have to multiply both sides of the equation by -2. Take -2, and I'm going to multiply it by 2x minus 4y equals 10. Okay, so that becomes -4x plus 8y equals -20. So that's the equation I'm going to use. I'm going to recopy these. So this one just comes down. I didn't do anything to it. 4x minus 8y equals 20. But I took this equation, the second equation, to the shop, sort of, and made this adjustment. It's all legal. It's all copacetic. So I'm going to put that there. And now I'm going to solve with the elimination, which simply means I'm going to now add both equations together. 4 plus -4 is 0. -8 plus, oh, that's 0 too. Well, that's weird. I eliminated both variables. And 20 minus 20, oh, that's 0. Well, I get 0 equals 0. What does that mean? Well, we're going to graph this, and what we see that this means that we actually have the same line. How often is 0 equal to 0? All the time. forever, infinite. So there's actually an infinite number of solutions. What we're going to see is the infinite number of solutions comes by what we were doing before, that these are actually the same line, aren't they? Uh, if I multiply the bottom one by 2, I get 4x minus 8y equals 20. I get the same thing. So they're just, they really are the same equation. The way I go about this, to listing all the solutions, right, just going back, it's really just one line. So I'm going to have x and I'm going to have its parameter. The parameter I get by taking one of these equations, and again, since they're the same line, it doesn't really matter which one I use, and I solve for y in this case. Solving for y parameterizes in terms of x. So we subtract 2x, 4y equals 10 minus 2x, and then we divide both sides by negative 4. Cancel out. And so we're going to get y equals 4. And I could just parameterize it that way. 10 minus 2x over negative 4. So choose a value of x, you will get a value of y. You can see you could do this infinite number of times. Let me keep those, and we'll go to the graphing calculator. Clear, clear. Showed in class how you could take that. We had a little smaller. There we go. That. Sorry about that. So we had, what did we have? We had 4x minus 8y equals 20. So you could actually solve that for, get into y equals form. What I found is you can just look at the equation. We have equals 20. So one thing you have to remember, put the parentheses first. So 20 is on that side. We had a 4x on the left-hand side. So when that comes over, we get that over there by subtracting 4x. And then we would divide both sides by negative 8. So I can write this, and this is how it's going to graph it. When I put in the other one, notice I have 10. I'm going to bring the 2x over, so it's 10 minus 2x divided by negative 4. So again, I put my parentheses. 10 is already on that other side, on the right-hand side. We subtract over the 2x, brings it over, subtract, and then we would have to divide by the number in front of the y, which is negative 4. That's that. I'm going to zoom 6, do a zoom standard. Gives me a standard size window because I don't know what's been in here. There's and it happened so quickly. It's nice that it's in color. You see it was a blue line, then it became a red line. One line's right on top of the other. If they were two separate lines, we'd see the intersections there. Okay, so graphically I see, oh yeah, there's an infinite number of solutions. We go with that. Okay, let's keep going. Here's an example. Again, we could solve this either way. I'll let you go ahead and do that. But what we'll do is we'll see that we actually need to change both equations. So you could either choose to get the 2 and the 5 to become the same number, or the 3 or the 4. So if we go with trying to eliminate the x's, what we look at is I need the coefficient to be the same number but the opposite sign. 2 and 5, I can't change 2 directly into 5 unless I use a decimal value. I can't change the 5 directly into a 2 unless I, again, use maybe a fraction. But I could change them both into 10, right? 2 times 5 is 10, 5 times 2 is 10. So what I'm going to do is take each equation. This one I'm going to multiply by, not 2, I'm going to multiply it by 5. I'll get 10x plus 15y equals 5. This bottom one I'll multiply by negative 2 because again I've got to get the opposite sign. Two times 5 is negative 10, and we see that cancels nicely. Negative 2 times 4 is negative 8y, and negative 2 times 6 is negative 12. So we will now eliminate these by adding them together. There's 0. 15 minus 8 is going to give us 7y, and subtracting 1, 5 from 12 gives us negative 7 by 7, right? We get y equals negative 1. That's one of our solutions. We plug that back in. 2x plus 3 times negative 1 equals 1, one of the equations, and then we can solve for x. So that's minus 3 equals 1. Add 3 to both sides, get 2x equals 4. 3 plus 1 is 4. And then we divide by 2, and we get x equals 4. So y is equal to negative 1, x equals 4. That's the solution to these equations. And again, if we graph these, that we would see that intersecting point of 4, negative 1. Okay. And this is as far as we got in class, so I'm going to hold off on this. And Friday we will pick up from here, and I'll have all my technology working, and we'll make that that continued video. But this will be enough for today because this is as far as we got, right? So anyway, look forward to working with y'all. Take care, and we'll see you Friday. And again, the virtual will be posted sometimes Friday as well.